Do you see the little live at the top of the, yeah,
Yeah.
do you see that? Okay. So if you click on the little arrow, you can copy the streaming link. You guys see that?
Okay. Yeah.
Okay.
Okay,
Yeah.
so I think, okay. So I think we give it another.
Start with the presentation, or will we be waiting for a few minutes?
I think we should maybe wait, maybe just one or 2 minutes, and then I'll introduce you and others as well, and then I think you get to start. Let's see. Okay, and that's the link. Okay, so perhaps before we get started, I can introduce our speakers and attendees today. Firstly, thank you everyone for attending this meeting today. It's oh, I see. That's interesting. Okay. Yeah, so our speaker today is Michael Hippke. Welcome. Thank you for being available to speak at this hour, which I believe is the early evening for you. Michael is a gentleman scientist, and since 2019 has been a visiting scholar at UC Berkeley with Berkeley Listen, and is also affiliated with Sonneberg University. And I would also like to introduce another person on our call, Peter McMahon, who prior to attending graduate school at Stanford spent a year at UC Berkeley working on instrumentation for radio astronomy and SETI, and is currently assistant professor at in applied and engineering physics at Cornell, researching physics of computation and how physical systems can be engineered to perform computation in new ways, with emphasis on quantum computation. So thank you also for being here. And Michael, if you would like to screen share, I'm not sure if that's if you are able to do that. Let me know if you have any.
Yes, thank you for having me tonight. I will try to start the presentation. So you should see my screen with the first slide. Can somebody confirm, please? Thanks.
Yeah, I can see it.
So good evening, everyone. My name is Michael Hippke, or Michael Hippke, and I like to start the presentation with a brief introduction of myself. Now that we are not meeting in person, I think it is always nice to give a little behind the scenes. I am 38 years old, I'm married, and I have 2 kids. I work a day job, which is not related to astronomy. And I'm currently working from my home office, which you can see here. This is close to Cologne or Düsseldorf in Germany. So most of my free time I spend with my lovely 2 little children. And I do astrophysics research as a hobby in my remaining free time, which is currently very little free time. So let us make the best out of it. So when it comes to astrophysics, I'm interested in various things, including exoplanets. For example, I developed a new algorithm to search for transiting exoplanets. It's called transit least squares. And that is about 10% more sensitive than any other known method. And during the last year or so, a total of 60 exoplanets were found using TLS. And the paper gathered about 50 citations in its first year. So I have used TLS myself and found 18 planets, and maybe there is more to come in the future. So on the SETI side of my research, I dived into a diverse range of topics, including launching rockets from super Earths, exotic particles. We will talk a little bit about that today. Solar sails, the cosmic microwave background with a short paper earlier this year. And I have some fun things on gravitational waves in the make for the future. But for today, we want to have a look at quantum SETI. So I published a paper in the astronomical journal called Searching for Interstellar Quantum Communications. That is currently at the proof stage, so I expect the real publication to happen in the next weeks. The title of the paper is an homage to the famous publication Searching for Interstellar Communications by Cocconi and Morrison, and I will come back to that in a minute. So what are we doing? What will we do in the next 45 minutes, or maybe 30 minutes? We'll see how fast it gets. If you look closely to the video screen, you may see the book on quantum field theory in the background in the bookshelf, which was written by my good friend Tony Z. But there you need not fear the word quantum today, because we won't do any quantum mechanics. There will also be zero math. There won't be a single equation. So, however, everything I say today will be firmly based on textbook science. So there are no dreams, no fantasies, and no nonsense. I'm convinced that I can explain everything in simple terms requiring no math. If anything is unclear, please post a question in the chat and then we can discuss it in the end. So what will we do today? First of all, I hope to spend the first about 5 to 10 minutes about what we tried in the past. And let me begin by saying that I really love traditional SETI, including radio SETI. And I think we should continue doing it. On the other hand, we have done decades of radio searches and found nothing so far. So I think we should try something additional, which is quantum SETI. I will explain today how to send quantum signals to the stars. And in the end, I will suggest a few experiments that we can do today already with current equipment and a search for such signals. So the idea to communicate with extraterrestrial intelligence was born in the 19th century. The first known proposal that I could find was made by the mathematician Carl Friedrich Gauss, who suggested to cut a giant triangle in the Siberian forest and plant wheat inside. His motivation was, quote, to make a correspondence with the inhabitants of the moon, end quote, because they and us would have in common some mathematical contemplations like triangles and other geometry things. And the interesting thing is that people have really tried doing this, also for other reasons. And that is clearly not the way to go. So such a passive message in the form of trees could be made brighter. Joseph von Littrow, another German fellow, suggested in the 1830s to dig trenches in the Sahara Desert, again in precise geometric shapes, and fill these with kerosene. And they would be lit at night and then signal our presence to the inhabitants of the moon. Now, I think Greta Thunberg would surely disagree with burning kerosene, but it would make a nice techno signature. There are actually naturally burning fires. Here, for example, is the door to hell in Turkmenistan, where natural gas is burning for decades. Of course, not in precise geometric shapes, but still it is a similar thing that's really happening. And when we move forward in time, the late 19th century was a time when many great canals were built on Earth, such as the Suez Canal and the Panama Canal. And then naturally, in that era, it was thought that similar projects would be undertaken by other advanced civilizations as well. And Schiaparelli announced the discovery of canali on Mars. As we know today, these are only wishful thinking, of course. A similar thing happened again when the radio was invented by Guglielmo Marconi in 1894. Shortly after, Nikola Tesla searched for radio signals, and surprise, surprise, he detected indeed coherent signals, which he believed to originate from beings on Mars. Again, this turned out not to be real. So traditional SETI started with the seminal paper by Cocconi and Morrison. Morrison explains their reasoning here, and I would prefer not reading it out loud, but I have the actual audio with me. I'm, however, not sure if this is being transmitted over Zoom. I will click on the play link and maybe somebody can signal whether it's working or not.
We cannot hear it, Michael.
So I hear it's not audible. So sorry for that. So the essence of the thing is that the two authors met and discussed whether to use gamma rays or radio waves. And the conclusion was basically to use radio waves because that's what they knew about. And there is one other reason. It's not only what they knew about, but it's also a bit of physics. So they get the more photons per watt argument in there, which I think is really important, and we will come back to that later again. On the other hand, it's what they knew at the time, of course. They could only work with what they had, and it is a funny coincidence in time that only a few months later, I think it was in the next Nature publication after theirs, the laser was invented. And then another 3 volumes later, the laser SETI paper by Schwarz and Towns was published. So all these things happened in a quick succession, one after the other. And of course, that opens the question, what's the right frequency? And maybe a big picture, to give a short big picture, are photons really the thing we should focus on? What about neutrinos? How does quantum SETI relate to the different particle carriers? So the question is, which particle is the best information carrier? And I did publish a paper on this, and I will not summarize it here, but just give a brief summary of what is the worst information carrier, from which we can then deduce what could be the best. So the worst of them all is the Higgs boson. You can see it here in the upper right corner, because it has the highest mass of all particles. And it is energetically the most expensive to propel to high velocities. Also, it has the problem that it decays in 10 to the minus 22 seconds. So if you really want to propel it to the next star and have it alive when it arrives, still in existence, then you need a lot of energy. And the energy to do that is so large that you would make a black hole out of that Higgs boson. So that's not the way to go. And in that paper, I did look at a few other particles. And in the end, the photon had real advantages over all the others with plausible assumptions. So for today, we will stick to the photons. On the other hand, quantum communication can be done with any particle. So that is more general. If you assume photon is not the right thing to do, then the quantum arguments still persist. So why, part 2, why would advanced beings communicate with quantum photons? Let us define the actual use case. First of all, quantum signals are not very useful for things like isotropic beacons. These isotropic beacons or lighthouse signals, they are most plausible at radio frequencies because this maximizes the number of photons per watt, as Phil Morrison said. For these lighthouse type signals, there is not much point in information efficiency and cryptography and a few other things that I will talk about in a minute. Instead, the use case for these quantum signals are targeted communications between two distant parties. That allows to have data links at higher frequencies, perhaps at optical frequencies. And again, with some plausible assumptions, as described in the paper, these beams are likely tightly focused and hard to observe by chance. So it is more likely to detect such a beam in case it is targeted at the Earth, at us. So this assumption of an optical beam targeted at the Earth, strictly it's not necessary for quantum SETI, but it's a plausible working assumption for what follows. So what are the advantages of quantum communications? I can think of 4, and these are information efficiency, gatekeeping, information security, and quantum supremacy. I will briefly go through all 4 of them. So the first is information efficiency. And here we see the usual pi-die diagram of photon information efficiency versus spectral efficiency. So on the horizontal axis, we have the photon information efficiency. I will try to use the laser pointer with the mouse. So here on this axis, measured in bits per photon. And on the other axis, the spectral efficiency here, measured in photons per mode. So in a simple example, you can send and receive photons with a temporal modulation, for example, with a nanosecond cadence, a simple photon counter. And then if you send 10 to the 9 photons per second, so 1 photon per nanosecond, you have 1 photon per mode, per temporal mode. So you're here on this, on the horizontal axis at the number 1, and number 1 bits per photon. And if you use something like a homodyne or a heterodyne modulation, you can encode about 1 photon, 1 bit of information per photon. In contrast, the quantum limit, which is shown here with the green line, would allow you to encode about 2.8 bits per photon. So that is some increase. And this quantum quantum limit is called the Holevo bound. The other curves that we see down here in gray, these are classical pulse position modulation trade-off curves. So this is a PPM-based classical communication. And when you always choose the optimum order for the PPM curves, you end up with this blue line here, which also symbolizes the classical limit in this pi diagram. And going from the classical limit to the quantum limit gives an increase of approximately 50% in pi. So you can encode about 50% more bits per photon with a quantum communication compared to a classical communication. Now that doesn't seem like much, but why would you waste it if you can do it with the technology? Or in other words, using classical instead of quantum communication is energetically wasteful. So switching back to the next slide. The second argument for quantum communications is gatekeeping. I got introduced into astronomy by John Learned, the great neutrino physicist, and he advised me on my very first paper. John Learned popularized the idea of interstellar neutrino communications and neutrino SETI in the 1990s. However, the idea of neutrino communications is already a bit older. There is a nice paper by Mieczysław Subotowicz, a professor of astrophysics from Poland. And he wrote that neutrino communication is so difficult that an advanced civilization may purposely choose it to communicate only with aliens at their own level of development. Now, let's see it this way. If there is a galactic internet that we could one day surf on, do you really want 1 billion monkeys spamming it with our chatter? So you can make communications very difficult by using things like neutrino communications. However, neutrino beams are very hard to focus and they are energetically very, very wasteful, as I did explain in that 2018 paper. So I think that's a very inelegant way to solve the problem of gatekeeping. It would be much more elegant to use photons, but use a gatekeeping method like quantum communications, so that only advanced civilizations beyond our own level could join. The third reason is information security. This is a big topic on Earth. And of course, we don't know whether it has a use case in a galactic internet or any interstellar communication. We don't know that. Today on Earth, if you want to communicate securely, people use classical information plus computational difficulty. However, for example, if we find a faster way to factor large prime numbers, we could break the RSA encryption algorithm. The problem with this classical cryptography is that there is no single mathematical function with a proven and large difficulty. So there are functions, there is no function for which it has been proven that it is very difficult. With quantum computers, we don't have to rely on these assumptions. With quantum computers, we would also be able to attack some of the cryptographic functions. Not all of them, but some of them. A more elegant way for secure communications is to use quantum cryptography. It relies on quantum mechanics and remains unbreakable as long as the theory is correct. Quantum cryptography is well established, and it has been shown in practice by many groups. So the fourth and last reason for quantum communications is quantum supremacy. When we start at today's internet, we see that it connects 1 billion or more classical computers over classical communication lines. But in the future, I think quantum computers will play a major role. And if you want to share your quantum computations with ET friends or friends on Mars or Alpha Centauri b, then you will have to use quantum communications to share these qubits. Okay, so if we decide to do quantum communications, who needs to do the quantum magic? Is it the transmitter? Is it the receiver? Or is it both sides? And it turns out that for 3 of the 4 use cases that we discussed, both sides need to go quantum. For example, to share quantum computing qubits, so the results of a quantum computation, both sides need a quantum computer, obviously. Also for quantum cryptography, and this has been demonstrated over large distances and through the air, both sides need quantum equipment. However, for efficient data transfer, and this is the use case of information efficiency, only one side needs quantum equipment. Personally, that was one of the things that surprised me the most. That was one of the things that I really didn't know when I started researching the topic. And there are many examples, and we will go through one later. For example, a squeezed light transmitter, so a quantum light transmitter, can be combined with a simple classical photon counter. And with this equipment, it is possible to achieve the Holevo bound of quantum communications. So this has been proven in the 1990s. It's a relatively new result. Let us have a look at what a quantum receiver looks like. I think this is what a lot of people are wondering about. What's a quantum receiver? What's a quantum transmitter? And I have brought a few pictures. And a quantum receiver must be different from a classical receiver. So on the right-hand side, this looks like magic, but it actually isn't. This is a classical photon counter. It is a superconducting nanowire single photon counter. So this is a mesh of metal that is cooled to very low temperatures. And when a photon hits that wire, the electric current in the detector changes. One could say that the photon's energy is transferred into electrons, which are then being measured. And in that process, the photon is essentially destroyed. A quantum detector or receiver, however, must not destroy each photon separately. So instead, it must measure an ensemble of photons, collectively, several of them. And that's where the name JDR comes from. This is an abbreviation for Joint Detection Receiver. And this really looks like magic. However, simple JDRs do exist in laboratories, and real experiments have been made. And some groups actually claim that their detectors surpass the classical Shannon limit. So the gap is closing, and I think we are inching towards the Holevo limit already. I have one picture with a nice illustration of what a quantum receiver could look like if you only use classical tools. Because one thing is that you can build a quantum receiver with only classical tools, such as beam splitters, phase shifters, and photon counters. So I will switch to the laser pointer function and illustrate this briefly. So on top, we have the photons coming in. So this arrow is a function of time. And at the first time here, a photon arrives, is being collected, is reflected by this mirror here, going that way. And here is a 50-50 beam splitter. So this is with a beam splitter with a ratio of 1/2. So 1/2 probability for the photon to turn right and the other half probability to go downwards. And here is the next beam splitter with probability 1/3 and so on. And these pink lines are memory modes. And not sure how to describe this illustration here. This is a pi phase shift. So these photons phase is shifted. And in the end, every output port has one of these very complicated Dolina receivers. And with this experiment, you can actually have a joint detection receiver that is sufficient for quantum communications. The problem with this is that in practice, you can do it for probing something, but for a real communication, this thing needs to get really big. So with high order ppm modulations in the thousands of photons, then you need a lot of tools, and there will be a lot of losses in all these beam splitters. So that's probably not the way that we can succeed in practice. More realistically, I believe we will need a quantum memory and a quantum computer of considerable size to make a good receiver in the future. So next, let us have a look at the quantum transmitter. The general understanding in the photonic information processing community is, quote, nobody knows how to do it. End quote. That is a statement by Saikat Guha, who is a professor at the University of Arizona. I saw many of his lectures which are available on his website, and they helped me to learn a lot about the topic. And of course, he is right at some level. There is no quantum transmitter on this planet. But I think there is a straightforward way to build one. Before we get into this, let us take one step back and review some common objections. So after the publication of the paper, I got a bit of feedback, and some people argued that we can't build a quantum transmitter. Also, there are statements that we don't have a quantum receiver, and thus we can't receive quantum signals. So some asked whether classical optical SETI shouldn't be sensitive to quantum light as well. After all, these are just photons. Let us tackle the transmitter question first, and then I will focus on observations with the equipment that we have on the planet today. So a powerful quantum transmitter with photons. Do we have one on this planet today? Now, if this were Microsoft Teams, I think we could use the raise your hand feature for those voting in favor of, yes, we have such a thing on Earth. I'm not sure if it is possible over Zoom. Is that possible? Somebody know? At least I can't see anything. So I'm a big fan of having these quick votes, but let's skip it in that case. So to answer the question, we need to make a definition first. What is quantum light? And so far, I have dodged that question entirely. And I did promise no equations in the beginning, but let us have a look at the figure from the paper. Here we see photon number distributions for different states of light. And in each of these plots on the horizontal axis, we have the number of photons per unit time, and the vertical axis is in arbitrary units. On the top left, we have a coherent or laser light, and this has a distinct temporal bunching compared to the thermal light. So top row in the middle, we have a thermal or chaotic starlight, which is strictly decreasing in the number of photons per unit time. Now the other four subplots are quantum states of light. The first is a Fock state with 5 photons. That is an idealized case, and you would have 5 photons per unit time. In the bottom row, we have amplitude squeezed light. At the amplitude squeezed state, this one has a denser distribution compared to laser light. In contrast, the phase squeezed state appears wider. And finally, on the bottom right, we have the pure or squeezed vacuum state. And that one is special because it has no contribution from odd photon number states. So we can now resolve this question I asked, whether there is a quantum light source on planet Earth. And yes, there is one. And the most powerful one that I'm aware of is located at LIGO, the Gravitational Wave Observatory. LIGO uses the squeezed vacuum light that we can see on the bottom right. The squeezed vacuum has a smaller phase fluctuation than the normal vacuum. At the same time, the amplitude fluctuations are larger, but that doesn't matter much because phase noise is what really matters for LIGO. They want to measure arrival times of the photons as precisely as possible. So they want to measure the travel durations of these photons, that is the path length of the interferometer. Here we have squeezed light at LIGO. We see LIGO on the right-hand side and an illustration of what happens with squeezing. So at the top rows, we have classical light, and in the bottom rows, we have squeezed light. On the left, it's the original fluctuations, and on the right side, an added signal. And you can see that the signal is much tighter because the noise is reduced. And squeezed light at LIGO is still quite new. There is a review paper by Roman Schnabel in Annalen der Physik. It was published last year. And Roman Schnabel wrote, quote, "Here I report on the historically unique situation that a new branch of astronomy depends on squeezed light for reaching higher sensitivities, while the comprehensive physical understanding of such light has still not been found." End quote. So let us have a closer look at how squeezed light at LIGO is produced. The light source. So first of all, there is still a classical laser at LIGO, and this squeezed light source is added to it through a second port into the arms. The quantum light source is in a box with a size of about 1 meter. You can see several people here handling this instrument. In the squeezed light source, there is an additional classical laser and a lot of equipment to control temperatures and so on. At the core of the device, there is a thing called optical parametric oscillator, or OPO. The OPO, I will switch to the laser pointer to show it. The OPO is under this clamp here. We will zoom in a minute. And the OPO converts one green photon into 2 entangled red photons. Switch to the next slide. So again, the OPO is this little thing here. You should see the red pointer pointing at it. What is the OPO? In the papers, you find an explanation that goes like, quote, "The central component is the subthreshold OPO, a traveling wave cavity built around a periodically poled potassium titanyl phosphate crystal." End quote. Okay, so what is it really? And I have one more picture with an even closer zoom to this machine, to the OPO. And here finally we get to the heart of the squeezed light source. We have this PPKTP crystal that is here following the yellow arrow. And it is clamped down close to this Peltier element that is for temperature control. So it works like this. Classical laser light travels through this crystal. And when it comes out, it goes through a lot of times, but when it comes out of the machine, having traveled 1,000 times through the crystal, then it has the quantum properties of squeezed light. Okay, and from my opinion and for for the scope and purpose of this presentation, that's all we need to know, and everything else is just technical jargon to make that work. Now, of course, that's how we produce squeezed light, a quantum light. And when it comes to an interstellar transmitter, which encodes actual information, there are certain aspects that are overlooked here. But that is, again, a topic for a different presentation. For today, We have reached a sufficient level of detail for this purpose. That is to show that it is possible to produce a quantum light on Earth. Okay, so quantum light can be produced. that is quite clear, I think. Every time, whenever LIGO is up and running, a few watts of squeezed light are running back and forth in its arms. Of course, LIGO's squeezed light source is not very powerful. There are at most a few watts going back and forth. However, in the future, for the next generation gravitational wave telescopes, this is hopefully expanded to a few kilowatt of power. And in comparison, classical lasers are at megawatt level. So when you look at the technological gap, that's about 3 decades. But in principle, I think there is no physical barrier for a big quantum laser. One day we will have one. So I hope I could convince you that a quantum laser is plausible. Let us now proceed to the receiver side. First of all, I'd like to come back to the question, can classical optical SETI detect quantum signals? And the simple answer, it's more nuanced in the paper, but the simple answer is no, it cannot. At least it's extremely insensitive to it. So classical optical SETI is usually either fast photon counting or a spectral search. This is one of the classical optical SETI signal assumptions. It's one of the figures from the paper showing a narrowband laser emission in a stellar spectrum. In contrast, quantum SETI loves large bandwidths. So for information efficiency, you want a broadband signal. And this is the signal assumption of quantum SETI. We can skip over the shape of that broadband signal that I hope to treat in a future paper in more detail. For now, it is only important to note that the quantum signal flux is spread over a large frequency range. And this is much more difficult to detect than just looking for peaks in a spectrum. I will come to better detection methods in a minute. Now, the other method, the other optical SETI method is fast photon counting. And that is very sensitive to weak lasers, which are tightly beamed, and the photons arrive in pulses. So for example, when a pulse arrives of order 100 photons per nanosecond per square meter, it is readily detectable in optical SETI instruments. However, optical SETI is not sensitive to even the brightest stars. So if you point the same detector at a bright star, it will detect nothing, because even Alpha Centauri will only send about 30 photons per nanosecond per square meter, and much less for weaker stars. So with these limitations, I believe that the search for quantum light should start with bright sources. We shouldn't start with the few quantum qubits that we could find somewhere. Instead, we should ask, are all stars really natural objects? Or are there a few objects that are in fact lasers? Quantum lasers? Quantum SETI adds a powerful new search vector to check for such photons, to check photons for their origin. We can ask, dear photon, are you natural or are you artificially produced? Now we get to the last and perhaps most important part of the talk. How can we detect quantum light? So the objection was we don't have a quantum receiver. In my paper, I present several methods, of which I'd like to highlight 3 in this talk: squeezed light, anti-bunching, and an interference test. All of these are possible with existing telescopes and equipment. So the first again is squeezing. We remember LIGO, squeezed light. There are many elaborate methods to detect squeezed light. However, just last year, a very simple one came to light. It was published in the Physical Review Letters, referenced here in the bottom right corner. And I must thank Jason Wright for helping me to download the supplementary material of this paper, from which I was able to learn and understand how that really works. And this method is quite simple because it only leverages the non-classical distribution of quantum light. So from these distributions, we saw that classical light has a linear relation between intensity and variance. This is shown here as a white line. And quantum light, however, squeezed light, however, has a quadratic relation. It's slightly different for squeezed and anti-squeezed, but a higher intensity correlates with a higher variance. So this distribution effect is quite small for reasonable squeezing factors of several decibels. It's only about 10 to the minus 5. But I did compare it to good CCDs, and good CCDs are about an order of magnitude more linear than what we are looking here. Also, an experiment with starlight should be quite straightforward because the calibration of CCD linearity is done regularly at every observatory. This is a method which is absolutely cheap because you can use any telescope with a CCD detector. If you point it at a star and make this plot, following the script that is provided by this paper in the physical review letters, you can tell whether this is starlight or a squeezed laser, a squeezed light laser. So next is the Hong-O-Mandel interference test. I hope I pronounce it correctly. This test only requires one 50% beam splitter and 2 photon counters at its outputs. And it is based on the argument that starlight has distinguishable properties. For example, it comes in random polarizations, different arrival times, and different wavelengths. In other words, every photon of starlight is different. These photons will then pass through a beam splitter randomly and are registered by the 2 detectors with about equal chance. This is in contrast to quantum light. Quantum light can occur in the form of indistinguishable photons. So these are photon pairs that are perfectly equal in frequency, arrival time, and polarization. And when you get a pair photon arriving at the detector, they will both take the same path. So in the bottom figure, with your photon detector on the left and the right exit port of the beam splitter, you would have both of them occurring on the same side. And you can then simply make a figure and plot the correlation of pair photons to determine how likely it is that you have detected pair photons. An experiment like this has been done with sunlight by Deng and colleagues 2019. And I think for SETI, we can do absolutely the same. We can use 2 telescopes and focus their light on each side of a beam splitter. A clustering on one side would indicate the presence of quantum light. So the third and last method for today is perhaps the most promising one. It's anti-bunching. This is a quantum effect known from intensity interferometry. 2 nearby telescopes which observe the same star show a temporal clustering of photon arrival times. And this correlation vanishes when the distance of the telescopes is increased. With this method, stellar diameters can be measured. Now, photon clustering is different for different types of light. When we plot this second order correlation function of photon arrival times, we see that chaotic starlight arrives tightly clustered. That is shown here in yellow. This is from a black body emitter. In contrast, when we detect a coherent classical laser light, we see a linear second order correlation function. So it's just a straight red line that we get here in the middle plot. Finally, quantum light is anti-bunched. So the photons are more equally spaced out. The arrival times between each subsequent photon are perfectly identical in the limiting case of perfect anti-bunching. And you would get a plot like this on the right-hand side in green. So the question is, of course, can we really measure this? And the answer is yes, we can indeed measure it. So photon bunching has been shown for our sun. On the left-hand side, we see 2 different lamps, and on the bottom, a diagram from observing our sun. And the same authors of this paper have also examined starlight, and they have injected laser light as a test for the sensitivity of their method. In their paper, they actually write that they are searching for natural laser emissions. I'm not sure if this is a genuine statement or a way to avoid saying searching for aliens. In any case, we know that it does work for the sun, which is a very bright light source. Now, the next question is, can we do it for fainter stars? And the answer is, again, yes, we can do that. So here we see the second order correlation functions for 3 bright stars, admittedly for 3 rather bright stars. But still, for all 3 of them, the second order correlation function is positive, exceeding the number 1 on this line. And so it appears that all of these stars are mainly natural objects, natural light sources. Okay, to summarize these methods, we can search for quantum light with our current equipment. My paper gives a few more ideas, and I'm sure there are additional methods to be discovered in the future. What can we do today? So we can check for squeezed light using just a CCD. We can check for indistinguishable photons with 2 telescopes and a beam splitter. And we can check for anti-bunch light with a photon counter and by calculating the second order correlation function. I will conclude the talk by saying what we should do next. We should start searching. Why should we start searching? Because fortune favors the bold. That is a quote by Pliny the Younger. With this, he described the action taken by his uncle, Pliny the Elder, when he decided to take his fleet and investigate the eruption of Mount Vesuvius in the year 79 AD in the Roman Empire. Pliny the Elder perished in the hot fumes of the volcanic eruption near ground zero, but the expedition gave a great paper about the destruction of the city of Pompeii. So my lesson from this is, without risk, there is no reward. Our risk today is to spend telescope time searching for quantum communications. Our reward is the discovery of a message from space. So thanks everyone, and I'm curious for your questions.
Thank you very much for an excellent talk. And I hope if anybody has any questions, please do feel free to ask them now.
Michael, Dan Wertheimer here. I was interested in your discussion of bunching, because we have experiments in SETI where we can time tag photon arrivals to about 100 picoseconds. And we don't have 2 telescopes maybe at the right distance. I was wondering, what would be the distance, a good distance between these 2 telescopes that you mentioned? Could you even do it with a single telescope, just looking at photon arrival times, or do you need 2 different telescopes?
I think you don't even need two telescopes strictly. I think that's the right mental image, that you have 1 beam splitter and 2 telescope feeding both sides. I think strictly it's not necessary. Now for doing intensity interferometry and measuring stellar diameters, so for typical stellar diameters and typical sizes like a few parsec and solar radio stars, you would need distances of something like 10 meters. There is the original publication, and I think they used something like more like 50 meters or so to resolve the stellar diameter. But it should work in principle with a small telescope as well.
Jill, do you happen to have a question, perhaps?
Yeah, Michael, I'm totally unclear about how you encode information in these systems.
So you refer to a quantum transmitter, how to encode information in a quantum transmitter?
Yes, and how to decode it at the receiving end.
Right. So I think the easiest example is that you just use a classical transmitter. So you just use any sort of pulse position modulation laser, and you do the magic, the quantum magic on the receiver end. You build one of these joint detection receivers, and the magic works that when you measure several photons in combination, you have lower noise. I think that's one of the mental images that helped me to realize that in classical light, you have always an uncertainty of the number of photons that you measured, whether it's 3, 4, or 5, or some number like this. And with a quantum receiver, you can reduce this uncertainty in the number of photons. So that is how you get more bits per photon in that unit of measure. That is one of the methods to increase the photon information efficiency. Or on the other side, if you insist on having a quantum transmitter and just a classical photon counter on the receiver side, the easiest mental image is that if you use a classical laser transmitter, you have you emit something like, I don't know, 5 photons. And there is a Poisson distribution, so you can't be sure whether you really emitted 5 photons. It could be 4 or 5 or 6 or something like that. And that gives you a related noise source that limits your photon information efficiency. In contrast, in a quantum laser, you could use a Fock state and make sure that you emit exactly 5 photons. So then it is sufficient to have a classical photon counter to count to 5. And that again reduces your measurement uncertainty. And that in essence improves the photon information efficiency. So you get more bits of information with the same number of photons, just through lower noise. Or a third visualization would be if you look at the LIGO noise curves, that you have a noise floor that is simply reduced by injecting squeezed light into the transmitter.
Michael, I got one more question. Are you familiar with Project Mania? It was led by Viktor Schwarzman in Russia. And they use a 6-meter telescope to time tag photons, and they were looking for a non-Poisson distribution of arrival times. I was wondering if you thought that project could have detected quantum communication.
I have only heard of the name, but have not read any detailed report.
It was a while back. You know, they're probably better timing experiments now, but it was an early one, and it was with a big telescope. I'll send you some papers.
Yeah, that would be great. Thank you so much. I think with increasing the timing accuracy, you get much more sensitive to quantum information. So with nanosecond photon counters, we are still about 5 or 6 orders of magnitude away from the limit. So if you go to picosecond, I think the best photon counters out there are something like 10 picoseconds. Not exactly sure. That is still maybe 2 or 3 orders of magnitude away from the limit, but it's getting there slowly. And I think if you look at the history, the last 3 or 4 decades of improvements of time tagging photons, we are still maybe 20 years away from reaching the limit, or 30 years, but it seems in reach.
I think we have, with these new detectors that have really good signal to noise, you know, they generate 1 million electrons per photon. We can actually do good centroiding and measure a few picoseconds. We don't do that with our PanoSETI experiment because we didn't think there was a need, but there's really good signal to noise for centroiding. Even though the pulse width itself is, you know, 100 picoseconds wide, we can centroid better than that. Anyway, it'd be interesting to follow up on that.
Great, thanks.
I had a quick question. So thanks for the talk. One of the things I was curious about is, especially when attempting to detect squeezed light and to determine signatures of whether the light you received was squeezed or not, one of the things that tends to be really important is how much loss there was between the transmitter that emitted the squeezed light and the receiver. Essentially, as you add loss or as you experience loss, you lose the squeezing is one way to think about it. You inject standard vacuum noise into your state. And so if you have too much loss, you will end up with a minuscule amount of squeezing that's very difficult to detect. So I'm curious what your thoughts are on kind of what would be the conditions for a very distant source to emit squeezed light and for us to still be able to detect it on Earth, given that there's kind of a finite, you're going to have finite spreading, and you have a finite detector size. So already basically some of the light will just miss your detector and so on. Just as sort of in general, if you could comment on this kind of practical consideration of what it would take to see it.
Yes, that is actually a very good question that is mentioned in the paper only briefly. It is so you are absolutely right that turbulence, atmospheric turbulence, can cause decoherence of these quantum coherence. So for squeezed light, I think it would be an interesting research project on its own. Honestly, I don't know how big the effect is, because LIGO uses more or less a vacuum in its arms. However, there are experiments that have been done through the Earth's atmosphere with quantum entanglement. So these are usually quantum cryptography experiments. For example, there is one famous experiment done by Anton Zeilinger between two islands of the Canary Islands over 144 kilometers of atmosphere. And I did briefly look into the interstellar density of dust and gas. And of course, there is some dust and gas out there, and the distances are so much larger than 144 kilometers. But if you multiply the numbers, it is much less of a column density between the Earth and Alpha Centauri than it is between the two islands of the Canary Islands. So if we can do quantum cryptography between two locations on Earth, then we can also do it to the stars. There is also one experiment done by a Chinese team using the reflection of a satellite. So they take a laser beam and reflect it off a satellite in orbit, and they can still prove that quantum coherence is still intact. So you get some decoherence, yes, but it would be interesting to analyze how much. That is an open question.
And it's maybe worth commenting that these experiments from Zeilinger and Xiaomei Pan's group and so on that are using long free space connections, there can still be a lot of loss, and those experimental schemes are somewhat resilient to loss because they're tending to use individual single photon states or entangled pairs of photons, where you can post-select on the successful events because you have a detector at each side, and if you detected two photons, then you know that you didn't have loss because you knew you only sent two in the first place. And so these single photon or photon pair-based experiments are much more resilient to loss than ones using squeeze states. With squeeze states, there's one intuition for it is that somehow you're more sensitive because you didn't know how many photons were sent in the first place, so you can't use this post-selection trick. So I think the proposals that rely on looking for photon statistics from either Fock states or maybe some other quantum states of light besides squeeze states have a good chance for being much more resilient to loss, in the sense that it's still not good to have loss because then you lost the photon, you never saw it in the first place, but at least when you did see it, you saw it. Whereas with the squeeze states, the loss essentially degrades the quantum nature of the light in the first place. But I agree with you that it seems like a good idea to try and analyze for each of these proposals, but especially in the case of the squeeze state one, what would be the impact of loss on your detection sensitivity, essentially, and what would be the loss sources that would contribute most? Because I think some of the sources you mentioned as candidates are important ones, but they're not the only ones. You also have essentially the divergence of the beam from the emitter in the first place. and the fact that your detector is not infinitely sized. But it sounds like an interesting proposal, and there's definitely some interesting calculations one could try do to determine the feasibility.
Yes, it is. I think you can tackle it both ways. You can calculate the things, and also you can test them experimentally. Even with a CubeSat class mission, you could put some simple laser to orbit and then try to establish a communication through the atmosphere. Or you do it in the laboratory in vacuum and then let some air in and test it over shorter distances first. So these are all things that can be tested in practice and actually measured, and then see what works best.
Does anybody else have any further questions for Michael? If not, perhaps if some questions do arise, perhaps you can make contact with Michael. I'm not sure if you. I think your contact details were available on the last slide, but I can also post those in the Slack if you would like. If there are no further questions, perhaps we can close the call. But thank you very much again for the presentation, and thank you for being available to speak at this time. It's your evening time where you are, and thank you to the others, and thank you also to Peter McMahon. Thank you, and hope to see you all again at our future meetings. Please look out for further emails announcing upcoming speakers. Thank you.
Thanks, everyone. Have a nice evening. Bye-bye.